You're watching a Channel 98 NBISD TV production.
Hey, welcome to Deja Vu. It's Algebra 2. It's that time of week again. I'm your host, Kevin Corpy, as always. And today, we've got a dandy of a program. You're going to get your money's worth today. Definitely, especially since you're not paying anything for this program. But we have to cram a lot of stuff in to a 30-minute window. So we're going to go ahead and get right to it. It's going to be about parabolas today. Parabolas, graphs, parabolas, equations. And what you need to accomplish by the end of the show is figure out how changing the equation ever so slightly will cause a change in the graph, okay? Because there's a correspondence there. Or how changing graphs will change the equation. You got to know it both ways, okay? Very important. So, I know you're asking at home, parabolas, what the heck is a parabola? Well, up to now in your math classes, you've been talking about linear equations, degree 1. Now, the degree of a polynomial is just the largest exponent on the variable term. So a line is of the form mx plus b, degree 1. They're straight lines, slanted straight lines. Kind of interesting, but kind of predictable, so maybe a little bit kind of boring. What we're doing today is we're going to literally step it up a degree, okay? And we're going to go to degree 2. That means that we're going to have x terms now that have an exponent of 2 on them. Very appropriate for Algebra 2. We're going to call those x squared terms. And the whole family of functions that have x squared in them are going to be called quadratics. Now, quadratic. Quad typically means 4. So I know you're thinking, if the degree is 2, why do we use quadratic? Well, it goes back to the Latin root where the word quadrantum meant to complete the square. A square has 4 sides. But if you look at a square, they're equal lengths on both sides. And if you found the area of that square, it would be the side length times the side length, which are the same. So you get side raised to the second power. And that's where we get side squared. So degree 2 are going to be quadratics, and their graphs are going to be parabolas. And you're going to see that they're going to be much more interesting than those slanted straight lines. They're going to actually have a little bit of curves to them. And they're going to put a smile on your face, hopefully, by the end of the show. Well, let me show you more specifically on paper the amazing world of parabolas. All right, lesson 11. We've got quadratic functions. They're going to graph as parabolas. We're going to look at their graphs and their properties. So what I was saying in the intro there is degree 1 linear functions are functions that you've been studying up to now. The degree is 1. They were x to the first power. So the degree was the largest exponent. We called those linear. We called them linear because their graphs all were slanted lines. Okay, so horizontal lines we call degree 0. Slanted lines that have slope to them we call linear equations. Well, today we're stepping it up. We're going to look at degree 2. We're going to be looking at forms of equations of y equals x squared, and we're going to call those quadratics, and the graphs are going to be parabolas. So notice how much more interesting these things already are. They've got a little bit of curvature to them, okay? Little happy smiley face. Math brings a smile to your face, okay? Now let's take a look at some other equations of x squared that have multiple terms behind the x squared. We can have a linear term, an x term, or a constant term trailing the x squared. So the first form we're going to look at is called standard form. There's a standard form of a parabola. We got f of x, of course, that's the function notation, equals a times x squared. So a is the coefficient of the squared term. We call that the leading coefficient. We have plus b, some number, times x, the linear term, plus c. Now, b and c themselves, either one of them can be 0, which means we don't necessarily have to have those terms present in the equation. Okay? But there's one stipulation here. To be a quadratic, a, the leading coefficient, cannot be 0. Think about it. If a was 0, then that term would be gone, and we'd be back with bx plus c, which would put us back at degree 1, linear. So a can't be 0. All right? So this is called decreasing order now. We have our x squared, the highest degree term, written first, degree 2. And then we have our linear term, degree 1. And then there's no x right here. So if you want to think about it this way, the c can be thought of as having an x, but it's to the 0 power. And x to the 0 power is a 1. So we have them written in decreasing degree, 2, 1, and 0. All right, let's take a look to see if we can figure out how to graph one of these guys. We've got f of x equals x squared plus 2x minus 1. So we know for sure that it is a quadratic because 2 is the largest exponent on any variable. Okay? And it is also written in decreasing order. 2, 1 on the x, and there's no x, so that's a constant degree 0. So the first way that you can actually see what a graph looks like is to create a table of values. Your independent variables are your x's, and we call them independent variables for a very good reason. We could choose them to be anything we want. So we just choose a nice little random sampling of it. I've chosen -3, -2, -1, some negative numbers. 0, of course, is a good one to use, and 1 and 2. I could keep going if I want. I can even choose 1s in between here, but these are really nice numbers. Now what we're going to do is we're going to plug these into the equation and see what we get as our outputs, our dependent variables, our y values, our function values. So if I plug a -3 in and I square it, -3 squared is -3 times -3. That's going to be 9. -3 times 2 is -6 minus 1. So that's going to give me a value of 2. So now I've created an ordered pair. It's going to be -3, comma 2. Okay? And I'll just proceed all the way down doing the same thing. What happens when I plug in a -2? What is f of -2? Well, it's -2 squared, which is 4, minus 4 minus 1. That's going to equal -1. So I have another ordered pair, -2, -1. And we'll proceed all the way through here. This is kind of routine calculations, and it's important to do it and to do it correctly. So you don't want to rush it. -1 squared is 1, minus 2 minus 1. That's going to be -3 plus 1. That's -2. So I have the ordered pair -1, -2. Plugging in a 0. Well, 0 is a really nice value because when x is 0, we are on the y-axis. So we call that the y-intercept when x is 0. That's an important point. And it's real easy if you have it written in standard form because anything that has a variable, in this case an x, is going to go away. You have 0 plus 0 minus 1. So we end up with -1. So that gives us the ordered pair, 0, comma, -1. And then plugging in a 1, we get the 1 plus 2 is 3. 3 minus 1 is 2. So I have the point 1, 2. And finally, plugging in 2, I get 2 squared is 4. Plus 2 times 2, that's another 4. So that's 8 minus 1 is 7. Okay, so I get the ordered pair 2, 7. Now, doing it this way is great. But first of all, how do you know which points to choose? How do you know when to stop choosing points? That's a good question. Experience is kind of the guide. We're going to learn a more efficient way to graph this too, by the way. So let's go ahead and plot these points. These points, -3, 2, down here. I got -3. I go left and up 2. Got that point. -2, -1. That's left 2. And down 1, so that puts me here. I've got -1, -2. That puts me down here. 0, -1 is right there. And then I have the point 1, 2, which is there. And then I got the point 2, 7, which is way up here. Okay? Now, do you notice anything about these points? If I was to connect them, it would form a nice smooth curve. And so that's what I want to do. So very carefully, this takes a little bit of practice, and you'll get better at it the more you work. And I'm sure your teachers will be happy to assign you lots of homework, so you get lots of practice. Now, the graph does not stop there. I only chose these points, and I'm drawing it in between there. But remember, this graph will continue on, forming the same pattern. Now, do you notice any type of symmetry to these points? Well, a line of symmetry is basically a line that we can fold this on so that it would coincide with itself, okay? Kind of like this. That line of symmetry is going to run right down the middle of this parabola. It's going to be a vertical line, and we call that the axis of symmetry. And the axis of symmetry is going to be a vertical line, so it's going to be of the form x equals. Now, how do we find what that value of x is? Well, notice that this point down here is the low point on the graph. We call that point a vertex. A line doesn't have a vertex. The vertex is basically where the parabola turns around. Okay, it's in this case a relative minimum. Well, the coordinate of that vertex, it appears to be -1, comma -2. Well, guess what? The line of symmetry, or the axis of symmetry, will always run right through the vertex, so that when you fold it along that line, it'll coincide with itself. So if it's going to be x equals, all we have to do is take the x coordinate of the vertex, which is -1. Now, here's a caution about a graph. It appears to me that my lowest point, my vertex, is at -1, -2, but how can I be sure? After all, it's just a graph. It's an approximation. Well, there's good news. There's a formula for finding the vertex, And here's what it is. The x-coordinate of the vertex is going to equal negative b over 2a. Well, what the heck is negative b over 2a? Well, it's going to be the a and b from the standard equation. If you have it written in decreasing order, a is the leading coefficient, b is the coefficient of the non-squared term. So let's look at our equation. X squared plus 2x minus 1. The x-coordinate of the vertex is going to be the opposite of b over 2a. And if I carefully plug in, my b is 2, so that's going to be the opposite of 2 over 2 times a. Well, what is a? In this case, it's an implied 1. So it's 2 times 1, or 2. If I simplify that, I get negative 1. That's the x-coordinate. Well, how would I find the y-coordinate? Well, the point, the vertex, is going to be at negative 1, f of negative 1. So we just plug that back into the equation. Well, we did that right here. When I plugged in a negative 1, I got out a negative 2. So yes, I have mathematically determined that the vertex is negative 1, negative 2. So this little equation right here, negative b over 2a, is very important to memorize. And a way to help you remember that, you've actually seen this before. This is the first part of the quadratic formula without the discriminant in the numerator. So negative b over 2a, you've seen it before. It's just in a smaller little version here that's more useful now. Okay, so standard form, very important. You can always pick points and plot it. Let's look at another form other than the standard form. It's going to be a little bit more useful for graphing. This form is called the vertex form. And it's called the vertex form because you can actually write the equation in this manner and you are staring at the vertex right in the equation. Not only the x value, but the y value. And here's what it looks like. F of x equals a, it's the same a as before, but it's factored out. X minus h, quantity squared, plus k. Now this is going to tie nicely to what we're going to be talking about a little bit later on the show. If you can write it in this form, this is a binomial squared. And this is plus k at the backside. So you notice your function is still something squared. So this is still a quadratic equation. But the nice thing about this is your vertex is going to be at hk. These two numbers in the equation. So it's going to be nice if we can write something like that. Well, what if it's written like this? This is what we started with in the last problem. This is standard form. The question is then, how can we convert something from standard form to this vertex form? Well, you've done it before. It's called completing the square. And I'm going to review with you how to do that. Completing the square is basically a nice mathematical principle of adding a clever form of 0. Okay? You can really multiply by a clever form of 1 and add a clever form of 0 without changing the value of an expression or an equation. And so that's what we're going to do. Now, the word clever means that there's going to be something to it. We can't just add 5 and take away 5. Okay? So here's what we do. We're going to start with f of x equals, we're going to write x squared plus 2x. We're going to take our squared term and our non-squared term. And we want to make sure the coefficient, the leading coefficient, is a 1. In this case, it is. Now, what I'm going to do is I like to put a little placeholder. I'm going to say I'm going to add something, and then I'm going to add something else right behind it. And notice I still can't forget about that little negative 1. Now, those blanks kind of give you a template that you can fill in. The key, though, is that these two things have to be a 0 pair, which means they have to add up to nothing. Now, how are we going to determine what it is we need to add there? Here's what we do. We are going to take half of this middle term. You take half of the b, and then you square it. Half of b, then square. So if you want to think about that mathematically, it's b halves quantity squared. So what is half of 2? Half of 2 is 1. 1 squared is 1. So what I did is I just added a 1. Well, now I have to add a negative 1, or the opposite of what I just added here. That's a 0 pair. Now here's math at work again. I can't, or I'm not going to, I can, but I'm not just going to subtract those right back out because then I'm no better off than what I started. By the associative property of addition, I'm going to group those three together. And if we've done it correctly, we have now created a perfect square trinomial. So this thing should factor into x plus, take the sign in the middle, and take half of that number, quantity squared, and then we just combine what's left out here. Negative 1, that's minus 2. And now I have a perfect square, a binomial squared. And if you go back to vertex form, a, h, and k, this number 1 is my a. This is not my h, okay, and I'll show you why here in just a second. Notice the x minus. That's part of the standard form. I have x plus. So what I need to do is actually rewrite this off to the side as x minus, putting it into that form, a negative 1 squared minus 2. Now I'm staring at my h, and this is my k. All right, so my vertex is at -1, -2. And here's the same graph from the previous page, -1, -2, the one that we did by hand. And now we know where the vertex is. If the leading coefficient is positive, as you're going to see later on in the show, in this case it's a +1, you know your parabola is going to be happy. It's going to be smiling. It's going to be opening up. Okay? If the leading coefficient is negative, if you're negative, what are you doing? You're sad. Your parabola is going to be opening down like a frown. Pretty easy. Leading coefficient will tell us which way it's opening. So if we know the leading coefficient is positive, we know where the vertex is now, it's going to open up. Now, the axis of symmetry again is going to run right through there. Here's another point that we can pick up pretty easily. Remember the y-intercept? All we have to do is let x equal 0. Plugging in a 0 into the standard form is a pretty easy thing to do. If you plug in a 0, you get 0 plus 0 minus 1. So I'm going to get the point 0, -1. And that's a real free, easy point that we can pick up that'll help us guide the shape of the parabola. Got it? All right. All right, a lot of information covered, still a lot more information yet to come. But we need a quick break, don't you? I need one. So go ahead and take one, watch these valuable public service announcements. But as always, while you're gone, ponder this. Which famous knight did King Arthur use to help him design his famous round table, huh? The answer when you return, and I hope you do.
The odds of a child making it to Broadway, 1 in 11,000. The odds of a child being diagnosed with autism, 1 in 150. To learn the signs of autism, go to autismspeaks.org.
All right, welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. Now, which knight did King Arthur have help him build his round table? The answer, of course, is Circumference. Yeah, that one's either funny because it's funny or it's funny because it's not funny. But it's funny. Let's get back to the math. All right, now for the fun stuff, the big stuff. We're going to learn transformations of parent functions. What is a parent function? A parent function in this case is our basic scaled down x squared, nothing behind it, parabola. It looks like a smiley face with the vertex at the origin. That's this right here in blue. Transformations means we're going to change it. We're going to shift it. We're going to move it in a different position. We're going to flip it around. We are going to reflect it across axes, and we're going to change its aperture. We're going to make it wider or narrower. Now, this is where changing the equation is going to manifest itself by changing the graph, okay, or manifest itself in the graph. And you have to know how the change is associated with the equation. So let's look at the first types of transformations. We got translations or shifts. Now, as the name implies, these just move the location of the graph. They do not change the shape. And there's two ways we can move these graphs. We can move them left to right, or we can move them up and down. Okay, so the left and right, the horizontal shifts, think of the horizontal axis as the x-axis, okay? So, excuse me, a change in the horizontal axis is going to be a change in x, okay? So let's look at this right here. We're going to look for values of h that are greater than 0, positive h values. Here's what the form looks like. It's x minus h quantity squared. Now notice that the function is the squaring function, something squared, that's x squared. We are now adding or subtracting something inside the function before we take the square of it, or square it. That's before we apply the function. Anything that has a direct effect on the x before you apply the function is going to affect the graph's x values. And in this case, if you're adding or subtracting, it's going to be a shift. All right, so let's look at this example. Right here in blue, I've got x squared. It's the standard parent function with the vertex at the origin. And I want to know now what's going to happen if I look at x minus 3 quantity squared. Well, let's rely back on the vertex form. Remember, if I add a 0 at the back there, I have my h and my k. That would tell me that the vertex now is at 3, 0. So in red right here, I put my vertex down at 3, 0, and that's really the only thing that's different. Okay, so what I've essentially done is I've taken my x squared graph and I moved it to the right 3 units. So this takes the graph and moves it right 3 units. Nothing else, okay, just a shift to the right. What about this one? What if it's x plus 3? Okay, notice that it's being added inside the function. That is before I square it. So that has to be a horizontal inside shift because I'm adding. Well, if we go back to the standard vertex form, x minus -3 squared plus 0, now h is -3 and k is 0. So my vertex is at -3, 0. So what have I done with my standard x squared graph here? I've changed the vertex and I moved it over to the left 3 units. Okay, so this was left 3. Now here's an easy way to remember it. Inside is x. Add, subtract, shift. Now notice on both of these, when it was minus 3, you have a tendency to think minus 3, that's negative, I'm going left. It's the opposite. If it's plus 3, you think positive, positive, right, right. It's the opposite of what it automatically or naturally appears to be. This would be left 3. And it's because the standard form is x minus, and we're looking at the number behind the negative. So just think inside x, opposite of what it appears. Got it? We're going to look at vertical shifts now. That is, we're going to move our parabola up and down, not left or right. Well, should look like a different equation, right? So we're going to look at a k value. That's the y coordinate of the vertex. We're looking at positive k values, okay? So I can have x squared. So notice I'm picking an x. I'm applying the function. I'm squaring it. So once I apply the function, squaring it, I got my y values in my hand. What am I going to do with those y values now? I'm going to add k to them. So that's going to take a y value here, and it's going to move it up. Or if I subtract k, it's going to move it down. Okay? Exactly what you would think it would do. So let's look at this here. X squared plus 3. Pick an x, square it, and that gives us our blue graph, the standard parent function. Now what we're going to do is we're going to take every single y value before we plot it, and we're going to add 3 to it. So notice what happens here. A 0 y value is up 3 units to 0, 3. A y value of 1, 1 is now up 3 units to 1, 4. So on and so forth all the way down the line. So this plus 3 is up 3. Okay? Up 3, exactly as it appears. What do you think happens to x squared minus 3? Well, we're taking our x, we're squaring it. So anything that we do outside the function or after we apply the function, in this case after we square it, is affecting the y values, the output values. The last thing we're going to do before we graph it is we're going to subtract 3. That should move your graph down 3. So here's our standard parabola, x squared. And if I move everything down 3, the y value of 0 goes down here to negative 3. The y value of 1 goes down to negative 2 on both sides. And so the entire thing is shifted down 3. We haven't changed anything other than the location. So this was down 3. Okay, so now we have a summary of our vertical shifts. Plus 3 outside the square, after the square, up 3. Minus 3 after the square, outside, down 3. Exactly as it appears. So inside's horizontal, opposite of what appears. Outside is vertical, exactly as it appears. Let's try it out here. Let's look at this example here. We've got a x squared, a parabola, written in decreasing order. And we've got it in standard form. X squared, x to the first, and a constant. What we want to do is we want to put it into vertex form and then sketch it using transformations. Okay, vertex form, we're going to know what the vertex is, but now we're going to shift our way of thinking in terms of horizontal shifts and vertical shifts. And since we know where our vertex is going to be, we'll be able to affirm our suspicions. All right, so to do that, we have to complete the square, remember. So I want to make sure that the coefficient, or the leading coefficient, is a 1, and it is. So I get x squared minus 6x. Now what I'm going to do is I'm going to put plus something, and then I'm going to put my plus 4. Remember what goes in the blanks? It's going to be a 0 pair, and it has to be something very specific. So we take half of the b, or the non-squared term's coefficient. Half of negative 6 is negative 3. Negative 3 squared is negative 3 times negative 3, which is positive 9. So I just added 9, so over here I have to add a negative 9. So that's a 0 pair. And again, I don't want to feel victorious and just quickly add those back together, because I get 0, and I'm no better off than before I started. So now what we'll do is we will associate the first 3 terms together. And again, if you did that correctly, you've created a perfect square trinomial, which will factor into a binomial squared. Square root of x squared is x. Square root of 9 is 3. And we take the sign of the middle term, which is negative, and it'll be that squared. And you could check by expanding it out. Negative 9 plus 4 is negative 5. So this is vertex form. Now let's go ahead and see what this does by transformation. This is a 3 being added or subtracted inside the function. So this should move the graph to the, at home, right 3. Remember, it's the opposite of what it appears. Negative 3, left. To the right. Okay? This minus 5 takes place outside the squaring function. So it's affecting the y values, the vertical values, and it's exactly as it appears. So this is going to move everything down 5. So how do we know that that's correct? Well, this is vertex form, remember. So the vertex is going to be x minus h. There's h. It's 3. and k is -5. So let's see if our vertex does end up being at 3, -5 when we move the graph of x squared right 3 and down 5. Here's how we're going to do it. There is x squared, okay, very proud x squared. Vertex is at the origin, positive leading coefficient, it's opening up, it's a happy parabola. What we're going to do now is we are going to move it right 3 and down 5. So if I put this red graph right on top here, here's what we are actually going to do. I'm going to move it to the right 3, so we can follow that right here. 1, 2, 3. So there's our new red intermediate graph. And then I'll take that one and move it down 5. 1, 2, 3, 4, 5. And the location of that red graph is the new graph. Well, look where the vertex is. The vertex is at 3, -5. So we know we did it correctly. Now at home you're probably saying you went right 3 and down 5. What if I went down 5 and right 3? Would I get the same thing? Good question. Let's see. If I start here and I go down 5 first, 1, 2, 3, 4, 5. There's my intermediate graph. And now I go right 3, 1, 2, 3. Yes, in fact, we end up with the exact same graph. And it's because the shifts, whether they're horizontal or vertical, both come from the operations of addition or subtraction. And you remember your dear Aunt Sally, right? Sweetheart that she is. She said that addition and subtraction come at the very end. But you don't have to do addition before subtraction. It just means that they have the exact same priority level. So you could do them in any order as long as you do them last. And since that's the only thing we're doing, we can do the horizontal shift or the vertical shift in any order that's pleasing for us. Now, in the equation, we typically write the vertical shift in vertex form at the end. So if you just want to get in the habit of doing things from left to right, you'll do the horizontal shift and the vertical shift. Okay? But realize that sometimes you might want to spice up the math a little bit and do it in the other order.
Deja Review.
Let's go ahead and summarize what we've done today. We've covered a lot of information. There's still 2 other transformations that I'm going to talk about on the next episode. Those are the reflections and the dilations. So today we talked about the standard form. So we had standard form, and that's going to be the parabola f of x equals, ax squared plus bx plus c. And what do we know about that? We knew that the vertex, or at least the x-coordinate of the vertex, was going to be, let me get rid of that, is going to be at -b over 2a. Okay? Or you could say the vertex itself will be at -b over 2a, that's the x-coordinate, comma, f of -b over 2a. Plug that value in. Okay, so that's the vertex. We also know that the axis of symmetry, the line that runs through the vertex, is going to be a vertical line, and it's going to be of the form x equals whatever -b over 2a is. That's standard form. Okay, and we write it in decreasing order, and remember up here, we know that a cannot be 0. All right, then we looked at something else. We looked at the vertex form. So the vertex form looked like this. Vertex form was the same parabola in general. We have f of x equals a times x minus h squared plus k. Now on today's show, our a was always equal to 1. Okay? That's going to be a different type of transformation that we're going to see next time. But what did we learn today? We learned that if a is positive, greater than 0, we're going to get a parabola that's opening up. It's a happy parabola. Okay? Now the vertex in vertex form that we get by completing the square is at h comma k. And so the axis of symmetry, which I'll call the AOS, it's still a vertical line. It's going to be x equals, we don't have to use -b over 2a anymore because we've got hk, and it's just the x-coordinate of the vertex. So it's x equals h. Now what else did we learn? Well, let's go back to that form down here. F of x equals a times x minus h squared plus k. We know that inside, that's going to be our horizontal shift. That's going to move the graph left or right. It's happening inside the function before we square it. And it's opposite of what it appears. Okay? So if h is 5, if this was x minus 5, it would move to the right 5. If this was x plus 5, that would move it to the left 5. Okay? This k out here was our vertical shift. And that moved the graph up or down, and it was exactly as it appears. It's affecting the y values. It is outside the square. So if this was something squared plus 5, it would move it up 5. And if it was something squared minus 5, it'd move it down 5. So we're going to start with just these two today. Go home, practice this, work a lot of problems, and as you're graphing them, make a distinct mental effort to ask yourself, how is a change in the graph going to affect the equation, and how is a change in the equation going to affect the graph? Transformations are something that you're going to experience at every mathematical level beyond Algebra 2. In pre-calculus it's huge, and on into calculus it's huge, and in higher level mathematics, the study of functions and the transformations extremely important. All right, we are definitely running out of time on today's show, and we covered a lot of information today. Hopefully you're getting the same information in your classroom. And if you have any questions about what we covered today, send me an email, or if you'd like to see this program again, order a copy. Just log on to the district website and contact our district offices, and we'd be happy to make you a copy of this program or any program that you see on Channel 98. A lot of fine quality programming there. Well, until next time, I am Kevin Corpy, and I'm reminding you as always to do your homework.